Once again, welcome to the series on linear programming. Throughout the series, we've developed an understanding of what linear programming is, and we've defined it as a mathematical technique to find the best solution from a range of possible solutions subject to constraints. We used linear inequalities to define and graph the constraints of the problem in order to find the feasible region. Then we found the best solution first by testing points in the feasible region and then by using a search line. Now we are ready to consider different kinds of problems. For example, what happens if we find a constraint that can be described by an inequality but it doesn't have an equal to part, an inequality in the form x plus y greater than a? Or what if the search line we use gives us more than one best solution to the problem? By the end of the lesson, you should be able to work with linear inequalities of the form x plus y greater than a, solve problems where the search line shows more than one solution, and use simultaneous equations to find optimal solutions. In this lesson, we are not going to use a context for the problems. We're going to focus on the mathematics of the problems. So, instead of working out what the constraints for the problem are, I will give you the constraints as linear inequalities in algebraic form. Let me show them to you. First, I've stated what the variables are. Let x be the number of units of A and y be the number of units of B. Then the given constraints are x plus y less than or equal to 12, 4x plus 6y greater than or equal to 28, y greater than x, and y less than or equal to 3x. Our first task is to determine the feasible region for this problem. We can do this by drawing the graphs of each constraint. Let's start by deciding how to use the x-axis and the y-axis. In other words, let's decide what scale to use on each axis. We want to be sure to fit the graphs onto the paper, but they mustn't be too small so that we can still read the details. If we know where each of the graphs cuts the axes, this will help us to decide on the scale to use. Now, let's look at the first constraint and consider the equation part of the inequality. That will be x plus y equals 12. The y value of the x-intercept is 0, so if y is 0, that leaves x equal to 12. And for the y-intercept, x is 0, so y is equal to 12. Now the second constraint. When y equals 0, 4 times x equals 28, so x equals 7. When x equals 0, 6y equals 28. Dividing through by 6 will give us 28 divided by 6, which is 14 divided by 3, or 4 2/3. And here's the third constraint, y greater than x. The line for y equals x goes through the origin and through 1, 1 and 2, 2. The line for the fourth constraint, y less than or equal to 3x, will also go through 0, 0. Now let's decide on the scale. The largest x-intercept is 12 and the largest y-intercept is also 12. So let's mark off the numbers from 0 to 12 on both axes. That will fit the graph paper well and will give us graphs that are big enough to read easily. Now we can draw the graphs for these constraints. By now, you should find this quite easy to do. Let me show you what you should end up with. The first graph goes through 12 on both axes. If we test a point like 5, 10, 5 plus 10 is 15, and that is not less than 12. So we shade this side of the line to show that these points are excluded. For the second constraint, the graph cuts the x-axis at 7, so we can plot 0, 7. It cuts the y-axis at 4 and 2/3. We could estimate where this is, but if the estimate isn't accurate, the line could go through the wrong points on the graph paper. So, to make sure that our line is accurate, we'll rather plot another point. Let's try an x value of 1 and work out what the y value will be. For the equation of the line, we'll get 4 times 1 plus 6y equals 28. Subtract 4 from both sides and we get 6y equals 24. So y equals 4. So when x is 1, y is 4. That point is easy to plot. Now we can draw the line through these 2 points. This method makes sure that our graph is accurate. Now we must still decide which side of the line to shade. Let's check this point, 6, 5. If we substitute this into the inequality, we get 4 times 6 plus 6 times 5. That's 24 plus 30, which is 54. 54 is certainly more than 28, so this point satisfies the inequality. We can shade the region on the other side of the line to show that those points aren't in the feasible region. Let's look at the next constraint, y is greater than x. This time the equality is not included. We must only consider points where y is greater than x. We can start by drawing the line for y equals x. That's the line through the origin and going through all the points where the x-coordinate is equal to the y-coordinate like this. This line represents all those combinations where y equals x. But now the inequality says greater than only, so the points on the line aren't actually part of the solution to the inequality. In other words, the points on this line won't be part of the feasible region. To remind ourselves that they aren't part of the feasible region, we draw a dotted line rather than a solid line. Again, we must decide where to shade. Once again, we'll take a point, let's say 3, 5. The y value is greater than the x value, so the point should be in the feasible region. So we'll shade the other side of the line. That leaves us with the last constraint, y is less than or equal to 3 times x. This goes through the origin. We'll need another point. Let's see what happens when x equals 2. Y will be 3 times 2, which is 6. So we can plot 2, 6 here and draw the graph through these 2 points. Look at this point 1, 6. 6 is greater than 3 times 1. So this point doesn't satisfy the inequality. We can exclude the points on this side of the line and show this by shading that area. Now that we have the feasible region, we need to find the optimal solution. But we don't have an equation to work with for this. We haven't been given an objective function yet. So, here is the question. maximize x plus y subject to the constraints. We are also told that x and y must be whole numbers. In other words, no fractions. So we must find the largest possible value of x plus y in the feasible region. We can make an equation out of this to help us find the answer. Let's use m for maximum equals x plus y. This is our objective function. Can you see what we need to do next? We can find the answer by testing points in the feasible region. For each point, we can substitute its x and y values into the equation m equals x plus y. Or we can establish a search line and use it to solve the problem. We're going to use a search line. Let's start by writing the objective function m equals x plus y in the form y equals something. That's easy because we just need to subtract x from both sides. That gives us y equals negative x plus m. Now we have the equation for a general straight line graph. The y-intercept varies according to the value m, and the gradient is -1. We'll start by drawing any line with a gradient of -1. If it goes through, let's say, this point 0, 3, then we can go down 1 unit from here and across to the right 1 unit. That takes us to the point 1, 2 here. The gradient of a line through these 2 points will be -1. The line we've drawn has a y-intercept of 3, but remember that this is a line we chose so that we can move it up or down until we find the maximum value in the feasible region. This line is our search line. We can move it up or down so long as we keep the gradient the same. That means keeping the lines parallel to the search line. We can do this with a ruler. If we slide the ruler over the graph, it passes through points in the feasible region. The y-intercept of the search line changes. It corresponds to the m part of the equation y equals negative x plus m. This is the value that we must maximize. We can use the y-intercept to show us when the value of m is largest, but still make sure that the search line passes through possible solutions in the feasible region. Now I'm going to move the ruler, always keeping it parallel to the search line and looking for the place on the graph where this line passes through the feasible region and gives the largest value for the y-intercept. The search line actually lies exactly on one of the boundaries of the feasible region. In previous problems, the search line helped us find one point that gave a maximum or a minimum. Now it lies on a boundary of the region and it goes through several points. Let's think about that for a minute. For each of these points, what is the m value? M equals x plus y, so here it's 3 plus 9, which is 12. And here it's 4 plus 8, that's also 12. 5 plus 7 equals 12, and 6 and 6 is 12. So they all give a value of 12 for m. Can you see any other point in the feasible region that could give a greater value than 12 for m? If there were a greater value, then we would have been able to move the search line further up the y-axis without moving it out of the feasible region. So what we have found is that there is more than one solution that maximizes the objective function. All the whole numbers along the boundary line here give a maximum value of 12 for m. From a mathematical point of view, these three solutions are as good as each other. But have a look at this point, 6, 6. If you look carefully, you'll see that it lies on a boundary line that was dotted. This was a dotted line to show that the points on this line are excluded from the feasible region. The constraint this line represents is y greater than x. So 6, 6 is not actually in the feasible region. Okay, so we've seen that it's possible to have more than one solution to a linear programming problem. We've also seen that the boundaries of a feasible region can be indicated with dotted lines to show that the equality is not included. Now I have another challenge for you. In the same example, I have this question to ask. Minimize x plus 4y subject to the constraints and with the limitation that x and y must again be whole numbers. In other words, no fractions. What this means is that we need to find the smallest possible value of x plus 4y in the feasible region. As in the previous example, let's write an equation for this. Let's call it d equals x plus 4y. If we want y on its own, we'll get negative x plus d equals 4y. So y equals negative 1x divided by 4 plus d divided by 4. This gives us an equation for a general straight line graph with a gradient of -1/4. But we don't know what the value of d divided by 4 is. So let's start by drawing a line here in the corner. If we use 0, 1 as one point on the search line, then for a gradient of -1/4, we need to move 1 unit down and 4 to the right. That takes us to the point 4, 0 over here. This gives us our search line. We can use this to find the optimal solution. Remember, we are looking for the combination of x and y that will give the smallest possible value for d. Let's use the ruler again. As we slide the ruler like this, it passes through points that are possible in the feasible region. The y-intercept of the line has the value d divided by 4. We're looking for the point or points in the feasible region that have the smallest possible value for d divided by 4. Look at this point that the search line passes through. Although it's in the feasible region, this point is not acceptable because it doesn't have a whole number value. Let's carry on. Here we have the first point, 3, 3, but it lies on the dotted line. This means that it's not actually in the feasible region, and so it isn't a possible solution. If we keep going, we get to this point, 2, 4. It looks like this is the first possible solution on our search line. This is the smallest possible combination of x and y in the feasible region. So we have minimized the value of y plus 4 times x at this point. Look at this solution. It is different from the optimal solutions we found in other problems. It is inside the feasible region. Our other solutions were all on the edge of a feasible region. But it's also the closest point to this edge of the feasible region, representing whole numbers for both x and y. What we've discovered here has been stated in a theorem for linear programming. The theorem says that the optimal solution will always be found at or near a vertex of the feasible region. Remember that vertex means a corner of a shape where two lines meet. Now, how do you think the solution would be different if we changed the objective function to 4x plus y and changed the limitations on the variables to real numbers? For a start, x and y can now have fraction values. The new search line will look like this. With this search line, the optimal solution will lie at this vertex here. Now we have another difficulty. It's not clear from the graph what the exact values of x and y are at this point. There's another way to find the exact values at the point of intersection of two straight lines. What do you think we can do? We can use simultaneous equations. If we can solve the equation for this line and the equation for this line together, the solution we find will be the point of intersection. And that's the task I'm going to leave to you today. Minimize 4x plus y subject to the constraints and x, y an element of real numbers by solving the simultaneous equations 4x plus 6y equals 28 and y equals 3x. To help you with this task, here are the constraints again. That brings us to the end of this series on linear programming. We have worked with all the important concepts of linear programming and solved several problems. Now you need to go and practice more examples of these types of problems.